In this problem, which is also a leverage problem, compared to the previous problem, that is problem number 4, there are 2 masses over here. So, that is why in the question itself it has been asked, we need to find out the governing differential equation, and specifically it has been asked to find out the transfer functions x1 of s divided by f of s and x2 of s divided by f of s. This is the problem given. We will consider one mass at a time, just like we have done it on previous occasions for spring mass damper system. Even here also we will consider one mass at a time and analyze it, write the functional block diagram and try to arrive at the governing differential equations as well as the transfer functions. Now, consider mass m1. Mass m1, it is applied with a force F. Mass m1 is applied with a disturbing force F, because of which it is getting displaced by a distance x1. Now, this mass is applied with a disturbing force F, because of which this is trying to get displaced by a distance x1. This is resisted by 2 components over here. See, a spring with a stiffness K1, a damper with a damping coefficient C1. So, this spring is offering resistance to the displacement of the mass m1 by offering the resisting force in the direction upward, which is against the direction of displacement x1. See, x1 is the force F is trying to pull down the mass m1 downward, because of which m1 is going to get displaced in the direction downward, whereas the spring that is connected over here, it is trying to pull back the mass m1. So, that is why it is trying to offer a resisting force to the displacement of the mass by a component of K1 into x1. Here we do not consider the distances as compared to this particular problem. Why? We are trying to consider the force where the spring as well as the force, both of them are present. Force is applied to the mass where the spring is also considered, the damping coefficient is also considered. We are not considering the effect of the force on mass m2. We are considering directly the mass where the force F is applied straight away. That is why the leverage analysis does not come into picture. It will be directly like a simple spring mass damper system for this particular, because force is applied to the mass and we are analyzing this spring mass damper system itself. So, therefore, the force F is applied onto the mass m1, which is trying to displace the mass m1 by distance x1. This is resisted by the spring by offering the resisting force of K1 x1 in a direction opposite to the direction of displacement. Then there is a damper with a damping coefficient of C1. This is also resisting. So, this is offering a resisting force in a direction opposite to the displacement again. So, I will write the force over here. The direction has to be upwards because the displacement is going to be downward. So, the direction of resisting force offered by the damper has to be the opposite direction. So, it will be upward over here. So, C1 into the displacement is x1. So, it is going to offer x1 dot as the resisting force. The damper is going to offer C1 x1 dot in a direction opposite to the direction of displacement. Now, to this functional block diagram, we will apply Newton's second law, which says summation of forces is equal to ma. So, m is m1 over here. A, see, the displacement is x1. So, obviously acceleration will be x1 double dot. So, m1 x1 double dot is equal to, see, the force is acting in the direction of displacement. So, positive with positive sign. See, minus c1 x1 dot, it is in the direction opposite to the displacement. So, minus c1 x1 dot. Then k1 x1 is in the direction opposite to the displacement. So, minus k1 x1. Now, bring all x1 terms onto the left hand side. See, minus c1 x1 dot minus k1 x1 dot becomes plus c1 x1 dot plus k1 x1, that is equal to, that will be we will be left with only f on the right hand side. Call that as equation 1. Then consider mass m2. Now consider mass m2. mass m2. See, the force F which is applied to the mass m1, it will also be experienced by the mass m2. In what direction? See, the force F is acting in the downward direction. So, obviously, here on m2, it will be acting in the upward direction, F. Then, what will be the total component of the force? See, it will be F into y1 is equal to F into y2. That is what is the analysis. See, F into y1, I will write it like this. Y1 into F will be equal to y2 into F. And now, if we want to find out this force, then if we name it as say F1 and F2, F1 and F2, then F2 will be equal to y1 by y2 into F1. See, for this mass, we did not go for extracting the force component in this fashion. Why? Because we were considering the mass for analysis where the force was actually applied. Whereas here, the force is not applied on mass m2, it is applied on mass m1. The effect of this force is trying to be found. We are trying to find the effect of this force on mass m2. That is why this particular analysis is important. The force experienced by mass m2 will be equal to F into y1 is equal to F into y2. We name it as, say, if this is as F1 and this as F2, y1 F1 is equal to y2 F2, and if we try to find what is the force experienced by the mass m2 over here, it will be equal to y1 by y2 into F1. So, disturbing force over here, it will be, if it is in the downward direction, here it will be in the upward direction because of the leverage mechanism. So, F, the disturbing force will be equal to y1 by y2 into F. Then, when this mass m2 is trying to get disturbed by force y1 by y2 into F, then what is the ultimate result? The displacement is going to be x2. This force, when it is been experienced by the mass m2, it is trying to pull the mass m2 by a displacement of x2. This is resisted by what? This is resisted by a spring alone. There is no damper present over here, spring alone. So, the spring is going to offer a resisting force in a direction opposite to that of displacement. So, spring with stiffness K2 is going to offer a force in the opposite direction to the displacement. So, K2 into x2. Since the displacement is in the upward direction, the spring force will be in the downward direction, that is opposite to the displacement. I will write this over here. Okay. So, now once we have written this, we have completed the functional block diagram. Now, apply the Newton's second law. Apply Newton's second law, that is sigma F is equal to ma. Now, what is m? It is m2. What is a? For this mass, x2 is the displacement. So, x2 dot will be the velocity, x2 double dot will be the acceleration. So, m2 x2 double dot will be the acceleration. That is equal to what? This is equal to whatever is acting in the direction of displacement with the positive sign. So, in the direction of displacement, what force is acting? It is y1 by y2 into F. See, y1 by y2 into F. Then, whatever is acting in the opposite direction of displacement, that should be with the negative sign. So, K2 x2 is in the opposite direction. So, minus K2 x2. Now, bring all x2 terms on one side. So, m2 x2 plus minus K2 x2, if we take it on the left hand side, it becomes plus K2 x2, that is equal to F into y1 by y2. Name this as equation 2. Actually, this is the governing differential equation for mass m1. This will be the governing differential equation for mass m2. Now, apply Laplace transformation to equation 1. When we apply Laplace transformation to equation 1, what happens is x1 will become x1 of s, x1 dot will become s into x1 of s, x1 double dot will become s square into x1 of s. So, when we apply Laplace transformation and then substitute the values, like I will write here, x1 is equal to x1 of s, x1 dot is equal to s into x1 of s, x1 double dot will be equal to s square into x1 of s. This will be the Laplace transformation. When we apply this to the equation 1, then this becomes m1 into x1 double dot becomes m1 s square into x1 of s plus c1 into x1 dot becomes c1 x1 dot is nothing but s into x1 of s. So, that is what we have written. Then k1 into x1 becomes x1 of s, that is what we have written here, that is equal to f of s. Now, what is the transfer functions asked? To be found out x1 of s by f of s. See here, the entire equation is in terms of x1 of s and f of s. So, therefore, you can take out x1 of s. When we take out x1 of s, we will be left with ms square plus c1s plus k1 on one side inside the bracket, that is equal to f of s. Now, what is asked to be found out? x1 of s by f of s. So, if we just cross multiply, we will get x1 of s by f of s, that will be equal to 1 divided by m1 s square plus c1s plus k1. This will be the first finding for us. First transfer function found out, x1 of s divided by x of s. Now, apply Laplace transformation to equation 2. If we apply Laplace transformation to the equation 2, what does it say? We will write it here like this. Let me make it more informative. Apply Laplace transformation to equation 2. What does it say? x2 will be equal to x2 of s, x2 dot will be equal to s into x2 of s, x2 double dot will be equal to s square into x2 of s. If we apply Laplace transformation to the equation 2 and f is equal to f of s, equation 2. Now, what is the equation 2? m2 x2 double dot, m2 x2 double dot is s square into x2 of s, this is what is written here. Then plus k2 x2. So, k2 x2 is nothing but x2 of s is equal to f into y1 by y2, y1 by y2 as it is, then f is written as f of s. Now, once we have written this, then you bring all x2 terms, you have brought all x2 terms on one side, take out x2 of s as common, you will be left with m2s square plus k2 is equal to into y2 x2 of s is equal to y1 by y2 into f of s. This is what is going to remain with you. Now, once you cross multiply, you are going to get x2 of s divided by f of s is equal to y1 by y2 divided by m2s square plus k2. This is what is the second transfer function that was asked to be found out. So, the entire problem is solved with that particular finding. So, there were two masses. One is a straightforward spring mass damper system where a force of F was applied onto the mass m1. m1 tried to get displaced by a distance x1. So, the displacement was resisted by the presence of a damper with the damping coefficient of C1 and the spring of spring stiffness K1. What we did? We wrote the functional block diagram, we applied Newton's second law, and then we found the governing differential equation. Thereafter, we applied Laplace transformation and then we arrived at the transfer function. Then for mass m2, we again wrote the functional block diagram, we applied Newton's second law, we arrived at the governing differential equation. Then what we did? We applied Laplace transformation to this equation 2, then we just iterated to arrive at the transfer function x2 of s divided by f of s. So, till now all the 5 problems that we have solved, they were based on the linear mechanical system, wherein whenever we applied a force, maybe with respect to a simple spring mass damper system, or it may be the leverage mechanism, the ultimate output was a linear moment of the mass. Now, as we spoke in the beginning of the sessions, mechanical systems could be of two types. One is the linear system, the other one is the rotary system. In the linear system, the output will be the linear movement of a body or some mechanism, whereas in the rotary system, the output will be the rotary motion of the body or the mechanism. Now, let us consider the rotary systems and try to analyze them so that we can arrive at the mathematical model, the governing differential equation as well as the transfer functions, and that could be easily demonstrated with the help of simple problems to be solved. Now, let us get into the problem number 6, which is a rotary system. As you can see here, the mass now takes up the shape of inertia I. Then the damper remains with the damping coefficient of C. Then the displacement which was happening in a linear system, now it will be the angular moment, which will be represented by the angle by which the I is going to tilt or rotate, that is given by theta. Now, the force which was disturbing, the force that was responsible for displacing the mass by some distance x, y or something, here in the rotary system, the force will be replaced by the torque, right. So, if you just see what are the similar terms compared to the linear system and rotary system is, in place of mass we will be considering I, in place of the displacement we will be consider x or y, we will be considering the angular moment, that is theta. Then in place of the force, linear force that was being applied in spring mass damper system, in a rotary system we will be considering the torque T. Then for the with the presence of damper, the damping coefficient remains C, whether it is linear system or it is a rotary system, and the spring stiffness that was happening, that was the linear moment of the spring which was offering the resisting force. Here it will be the twisting force of the spring, that will be represented as KT. So, in the spring mass damper system or a linear system, the spring stiffness was termed as only K, the spring stiffness K, whereas here in the rotary system, the spring stiffness is termed as KT. Now, this is the given system problem. In this problem, this is the rotary system what has been given to us, and we are asked to find the governing differential equation as well as the transfer function. This procedure remains the same, 100% same as was to be on the previous occasions. First we will have to write the functional block diagrams, then we will have to apply Newton's second law, then we will be arriving at the governing differential equation. Thereafter we have to apply the Laplace transformation to the governing differential equation so that we can arrive at the transfer function. Now, what is the transfer function? See, in any of the problems, right from the problem number 1 to the problem, the last problem in this particular chapter, in the beginning itself we have to plan the solution. We have to we have to know what is the transfer function that we are trying to arrive at, right, whether it is y of s by f of s or y1 or x1 of s by f of s, whatever, what is the transfer function we have to arrive at. If we are able to keep that in mind, then the plan of the solution will be more or less accurate. That is where we will be arriving at the actual results that we have to obtain. Here in this system, you can just see what could be the transfer function we need to find. Just one analysis, quick analysis. What is the transfer function we are trying to arrive at? What is the output from the system, rotary system? It is the disturbance, the angular moment or rotary moment. By what angle the body is getting disturbed, that is what will be the output. So, here theta is the angle by which the body is going to be rotated. So, theta is the output. Why it is rotated? Because the body was applied with a disturbing force. In case of rotary systems, torque will be the disturbing forces, whereas in case of linear systems, F force was the disturbing component, whereas in the rotary systems, torque will be the disturbing components, resulting in the rotary motion of the body, that is measured by the angle theta. So now we have to, if we just try to know what is the transfer function that we are trying to find here, it will be the output by input. Output is theta, input is torque. So theta by T will have to be the transfer function for this rotary system. Now given rotary system, first we have to write the functional block diagram. See, so first we will try to write the functional block diagram. That is the first step. The procedure does not change. Functional block diagram. In place of mass, it is I now, so I will write I as it is. It is disturbed by the torque T. Whichever side the disturbing forces and the components are present, on those sides only we have to write the resisting forces as also. So the disturbing force, the disturbing component is torque T. What disturbance it is causing? It is causing the inertia I to be rotated by an angle theta. So there is an inertia I which is disturbed by a torque T, resulting in the rotary movement of the body by an angle theta, right. Now to this disturbance, what is there to resist? So we have a damper, we have a spring. Damper is going to offer the resisting component, velocity component of the resisting force in a direction opposite to that of the disturbance. What is the disturbance here? Theta. So this is the disturbance. If the damper has to offer a resisting component to resist the angular motion, then it has to offer in this direction. This is in a direction opposite to that of the disturbance. Okay. So this will be C and displacement is theta, that is why it will be C into theta dot. Then there is a spring present here on the right hand side of I. This is also offering a resisting component to resist the rotary motion of the inertia I by the angle theta. So here it will be in this direction, and then what is the direction I have to write? If theta is, this has to be written with a direction opposite to that of theta. So this is what will be the direction. So it will be kT into theta. Damper offers velocity component of the resisting force, whereas the spring offers the displacement component of the resisting force. That is why damping force will be written as C into theta dot and the spring force will be written as kT into theta. And both of them are offering the resistance in a direction opposite to the disturbance. Disturbance is theta. In whichever angle theta will be present, opposite to that, these two components will be offering the resisting forces. Okay. Now, once we have written the functional block diagram, we have to apply Newton's second law onto the functional block diagram. So if it is a linear system, it will be sigma F is equal to ma. If it is a rotary system, it will be sigma T is equal to I alpha. Just like A was representing the acceleration, here alpha is representing the acceleration component in the rotating body. So this could be further written as sigma T is equal to I theta double dot because theta is the disturbing component and disturbance, so theta double dot. Now I theta double dot is equal to, just like we used to write all the forces acting in the direction of displacement with a positive sign, all the forces acting in a direction opposite to that of displacement with a negative sign, the same thing is applicable here also. Now I theta double dot is equal to what forces, what components are acting in the direction of theta? It is only T here. So T is written with a positive sign. Then C theta dot is acting in a direction opposite to that of displacement theta, that is why it is minus C theta dot. Then kT into theta, again it is acting in a direction opposite to that of theta, that is why it is minus kT into theta. Okay. Now this can be rewritten as, bring all theta components on one side. See I theta double dot minus C theta dot becomes plus C theta minus kt into theta becomes plus kt into theta if we take them on the left hand side, leaving only t to be there on the right hand side. This is the governing differential equation. This is the governing differential equation. Now apply Laplace transformation onto this governing differential equation. What it means to say by Laplace transformation? It is t is equal to, it can be t of s, theta is equal to theta of s, theta dot is equal to s into theta of s, theta double dot is equal to s square into theta of s. Now if you substitute the Laplace transformation into the governing differential equation, so I, we have written I as it is, theta double dot becomes s square into theta of s, s square into theta of s. Likewise, C as it is, theta dot is written as s into theta of s, and then kt into theta, it is written as theta s of kt is equal to t of s. Now we in the beginning of the solution itself, we knew that the transfer function has to be for this system theta of s divided by t of s. So take out theta of s common, you will be left with is square plus cs plus kt, and you will be left with the ts on the other side. So just cross multiply, you will get theta of s divided by t of s is equal to 1 by is square plus cs plus kt. This is what is the transfer function that we were trying to arrive at. The next problem is again just like in the spring mass damper system. The problem number 1 was single mass spring damper system. The problem number 2 and problem number 3 were with multiple masses. Likewise, even in the rotary systems also, there need not be only one inertia I, there can be multiple mass, just like multiple masses, there can be multiple inertias. So here what is asked here is, we need to find, it has not been asked to find the transfer function, it has been asked to find the governing differential equations. Just like in the multiple spring mass damper systems, we considered one mass at a time. For each of the mass, we wrote the functional block diagram, then we applied Newton's second law, and then we arrived at the governing differential equation. And then in a similar fashion, even for this problem also, we have to consider one inertia at once, write the functional block diagram, arrive at the governing differential equation. Now, to begin with, let us consider I1. I1. See, I1, there is no disturbing component, there is no torque that has been given here. Instead, there is it is connected with this I1 is connected with the spring with stiffness of Kt1 as well as the damper with damping coefficient of C1. So I1 is somehow, maybe natural, is somehow getting disturbed by a rotary motion of the angle theta 1. Now to this disturbance, what is resisting the disturbance of I1 by an angle theta 1 is the spring as well as the damper connected with I1. So therefore, spring, since it is on the left hand side, we will write left hand side, but we will write it on the in the opposite direction to the theta 1. Why? Because this spring is trying to resist the rotary motion of the body by an angle theta 1. So the spring offers the displacement component in a direction opposite to theta 1. So Kt1 into theta. This is what is the resisting component for I1 offered by Kt1. Then on the right hand side there is a damper. In what direction it is acting? It is acting in a direction opposite to that of theta 1. What is the magnitude of the force it is contributing to resist? It is C1 into theta dot, theta 1 dot. This is what is the functional block diagram for I1. Now to this functional block diagram, apply the Newton's second law. What does it say? Sigma t is equal to I theta double dot. So what is I? It is I1. theta double dot is theta 1 double dot. Then what is acting in the direction of theta 1? There is no force, there is no torque. What is acting in the opposite direction to theta 1? C1 theta 1, so negative sign. Sorry, here there is correction, here there is a small correction. The resisting component offered by the damper, since damper is connected to both I1 as well as I2, just like spring mass damper system, even here C1 theta 1 dot minus theta 2 dot is the resistance offered by the presence of damper. Why? Because the moment I1 tries to rotate by an angle theta 1, what happens is the damper will try to resist that rotation. When it tries to resist that rotation, it is again that resisting force of C1 theta 1 dot is resisted by I2 with a spring damping force of C1 theta 2 dot. So, the effective resistance offered by the damper, it will be equal to C1 theta 1 dot minus C1 theta 2 dot. So, effectively it will be C1 of theta 1 dot minus theta 2 dot. That is what we have written here. The same will be written here. Since it is in the opposite direction to theta 1 with negative sign, this is also KT1 theta 1, this is also in the opposite direction to theta 1. So, that will also be with the negative sign. Then since we are considering I1 and theta 1, bring all theta 1 component on one side, retain rest of the components on the other side. This will give us the governing differential equation for I1. Now, similarly, consider I2. When we consider I2, see, I2 is trying to rotate by an angle theta 2 in this direction. This is resisted by what? This is connected with C1, this is connected with KT2 also. So, those two, the damper C1 as well as spring with stiffness KT2, they will try to resist the movement of I2 in a direction of theta 2. So, the damper C1 will offer the resisting component C1 into theta 2 dot minus theta 1 dot. Then the spring present on the other side will offer resisting component in a direction opposite to theta 2 with a magnitude of KT2 into, see, this spring is again connected to I2 as well as I3. So, therefore, the resistance offered by KT2, it will be equal to KT2 into theta 2 minus KT2 into theta 3, because it tries to resist the movement of I2 by KT2 into theta 2. Again, it will be rotated back by a magnitude of KT2 into theta 3. So, therefore, the effective resisting force or component offered by the spring, this spring, will be equal to KT2 theta 2 minus KT2 theta 3, that is KT2 into theta 2 minus theta 3. This will be the resistance offered. Now, to this functional block diagram, apply Newton's second law. I sigma t is equal to I theta double dot. I will be I2, theta double dot will be theta 2 double dot. Then that will be equal to no force in the direction of theta 2. So, nothing with positive sign. Therefore, the C1 into theta 2 dot minus theta 1 dot is in the direction opposite to the theta 2. So, with negative sign. Then this force is also in the opposite direction to the displacement or the rotary movement of theta 2. So, this will also be with the negative sign. Now, since we are considering I2 with a displacement with a rotary motion of theta 2, we will try to bring all theta 2 components on one side. That is what we have done here. Therefore, we will get the governing differential equation for I2 as this equation. Then lastly, there is I3. So, consider the inertia I3. I3. This is trying to get rotated by an angle theta 3 in this direction. Now, to resist this rotation, what do we have here? We have a spring KT2 connected to both I3 as well as I2. So, because of which when I3 tries to get rotated by an angle theta 3, this is resisted by the spring with an effective force of KT2 into theta 3 minus theta 2. So, on the left hand side, spring is resisting, but in the direction opposite to the displacement. So, KT2 into theta 3 minus theta 2. Then, on the right hand side, there is a damper with a damping coefficient C2. This will offer resistance to the rotation of I3 by an angle theta 3. Therefore, this is going to offer C2 into theta 3 dot. This is not connected to any other inertia. That is why it will completely contribute to resist the rotation. So, it will be, its direction will be opposite to that of theta 3. So, C2 into theta 3 dot. This will be the force. Now, once we have done with the functional block diagram, apply Newton's second law. Sigma t is equal to I theta double dot. I is nothing but I3, theta is nothing but theta 3 double dot, that is equal to, there is no torque, so nothing with positive sign, and resisting forces are in the opposite direction. So, C2 theta 3 dot will be with negative sign. KT2 theta 3 minus theta 2, that will also be with the negative sign. So, therefore, you just bring all theta 3 components on one side, rest retain it on the right hand side, you will get the governing differential equation. So, this is how we have solved as many as about 7 problems in mechanical systems, in both linear systems as well as rotary systems. We went on from the simplest of any linear system, such as a single mass spring mass damper system, wherein we tried to know how to write the functional block diagram. We applied Newton's second law, then we found out the governing differential equation. Then we applied Laplace transformation, whereas degree of the components of the equation were brought down to single, and then we derived the transfer function. Then that was with single mass system. Then we went on to derive the transfer function as well as the governing differential equation for two spring mass damper systems connected, and then we went on to learn how to arrive at the governing differential equation of a system which was having more than 2 masses. Then we went on to solve the mechanical systems, that is the leverage mechanisms which were there. 2 problems we have solved there. Then we also learned how to arrive at the governing differential equation as well as the transfer function for the rotary systems. That completes the learning of arriving or deriving the governing differential equation as well as the transfer function for the mechanical systems comprising of linear systems as well as rotary systems. Thank you.